So the perceptron. So remember, h of x is the sign of w transpose x. How many free parameters? So you have w0, w1 to wd, so d plus 1 free parameters. Okay, and indeed, theorem. Okay, the VC dimension, so dVC for the perceptron in d dimensions is equal to d plus 1. Nice. Okay, it's equal to the number of free parameters, and it's pretty small, and it's pretty much, you know, the best you could have expected if you are in d dimensions. Because if you're in d dimension, if you have any non-trivial hypothesis set, it's going to have at least d parameters that you need to specify in order to specify its behavior in each dimension. Okay, so you can't really get away with less than a complexity of d, and the perceptron achieves this d plus 1, you know, complexity. Okay, so the error bar is basically related to the dimension. So for the perceptron, E out of G is linked to E in of G plus, you know, order of the square root of the dimension times log n over n. That's nice. Okay. So if you have more and more features, then to effectively learn a perceptron, this is what the theory is telling you. If you have more and more features, in other words, you're going into higher and higher dimension, to effectively learn a perceptron, you need more and more data to keep control of this error bar. And we can tell you, we can quantify how much more we need. Okay? So proof. So this is a deep result. So in fact, not only is the perceptron the model that, you know, I'm recommending, but it's part of what we're going to call the linear models. But, you know, all other complex models are built from the perceptron, like neural networks. So it's just a very fundamental model, and it is a good hypothesis set. In particular, it's a very good hypothesis set because, you know, the VC dimension is small. Okay, it's small and gives you a very tight link between E in and E out. So if you can get E in close to 0 with the perceptron, bam! You have learned. You have learned well. It's only when you have to go more and more complex than the perceptron in order to get E in close to 0 that you need to start getting worried. Okay? All right. So the proof. I've done enough theory already. Okay? So this is left as an exercise for the reader. In particular, it's going to appear as one of the exercises on your homework. But I'm going to give you some hints. So we need to prove that the VC dimension, dVC, is equal to d plus 1. Well, you know, I'm suggesting that you do this in 2 steps. So we can do this in 2 steps. The first step is to show that the VC dimension is at most d plus 1. And then to show that the VC dimension is at least d plus 1. Okay, and if you can show that the VC dimension is at most d plus 1 and it's at least d plus 1, okay, then, well, basic math, it has to be equal to d plus 1. Okay. So let's discuss how we show these things. So remember, let me remind you, the VC dimension, dVC, is equal to the max number of data points that you can shatter. Okay, so to show that the VC dimension is at least d plus 1, you have to show that the max number of data points that you can shatter is at least d plus 1, which means that it suffices to show that you can shatter d plus 1 points. So you can shatter d plus 1 points. Okay. And does it mean that you can shatter any collection of d plus 1 points? No. You can shatter some collection of d plus 1 points. So it suffices to exhibit a single collection of d plus 1 points that H can shatter. So in other words, it suffices to exhibit a single collection of d plus 1 points and argue that it's possible to choose the weights. So, and argue that for every dichotomy, so for every one of the 2 to the d plus 1 dichotomies, it's possible to choose the weights W such that you can implement that dichotomy. Now, because we're in this abstract d plus 1 dimensions, you have to make this argument mathematically, linear algebraically. Okay. Now, what about to show that the VC dimension is at most d plus 1? Well, here, okay, you have to, so remember, the DVC is the maximum number of data points that you can shatter. Okay. So, we're claiming that the maximum number of data points that you can shatter is at most d plus 1. Well, what does that say about d plus 2 points? It says that d plus 2 points cannot be shattered no matter how you arrange them. So, you cannot shatter d plus 2 points no matter how you arrange them. Okay, that's what it means. And so in order to show this, this is tough. You're going to have to dig deep into your linear algebra vault to show this. Okay, so you have to show that, you have to sort of play an adversarial game. The best way to show this is to play an adversarial game. Give me any d plus 2 points. So give me any d plus 2 points. And now show that you can construct a dichotomy that's provably not implementable. Okay, so given any d plus 2 points, show that, or construct a dichotomy that is provably not implementable. In other words, given any d plus 2 points, because you have to make your argument general. That's why this is a harder thing to prove. Here you just need to find a specific d plus 1 points that can be shattered. Here you have to show that no matter how you choose d plus 2 points, okay, I will be able to find a dichotomy. Now that dichotomy might depend on the specific d plus 2 points, but no matter what d plus 2 points you give me, I will be able to find a dichotomy and prove to you that this type of function, no matter how you pick the weights, cannot implement it. It's a hard thing to prove. Okay. Like I said, it's going to dig deep into your vault of linear algebra. Okay. All right. So, let's move on to sort of more practical, sort of implications, links between this theory, this generalization error bar, and what we will face when we actually face a machine learning problem. And I'm willing to spend, so this is the, so we're going to now start discussing in more detail the approximation generalization trade-off. So first we'll look at how that's embedded in here, and then we're going to look at this other approach, which is the bias variance analysis. And that's because approximation versus generalization is so important, okay? Because that's all there is in learning. Okay, that's all there is in learning. It's important to understand. That's all there is in learning. You can see E in, but that's no good to you unless you have the link to E out. And in building this link to E out, while also simultaneously trying to minimize E in, that's where this approximation generalization trade-off, surfaces. And it's there always. You cannot avoid it. So you had better, confront it head on and deal with it. Okay. And that's what we're going to discuss. It's embedded in here, and it's also useful to have another way to look at it, which is called the bias variance analysis.